This section describes the pre-processed data task within the prepare data step of the ML lifecycle. As illustrated on the slide, the steps of data preprocessing, feature engineering, and model development are all iterative and intertwined. Data preprocessing puts data into the correct shape and quality for training. With ML data processing, it's mostly the data scientist's role to prepare and wrangle the data. Their activities are similar to the data wrangling steps that were presented in the ingesting and preparing data module. But ML preprocessing includes activities that are specific to preparing data for ML models. The data scientist might also request updates to the transformations that are included in the data collection process, if their exploration of the data suggests that changes would benefit the processing. An important component of the data preparation step is the analysis and visualization of the data as it's being explored and processed. Exploratory data analysis, or EDA, with visualization tools can help a data scientist to quickly gain a deeper understanding of data. This helps to identify patterns that are not evident by looking at data in tables. Data scientists might employ a variety of tools to serve this purpose, some of which let them combine data exploration, wrangling, and interactive analysis and visualization in an integrated way. Many data preprocessing strategies exist, including those listed here. Data scientists would apply the appropriate strategies based on the dataset and the intended use case. This might include a variety of statistical modeling techniques or steps, such as creating rotated or resized versions of an image to augment an existing set of images. Many of the individual strategies that are listed actually contribute to the important strategy of balancing or unbiasing data. To produce accurate predictions, it's important that the data scientist identify and mitigate bias in the data. For example, if the goal is to predict outcomes for a global customer base, but the dataset includes a large percentage of samples from one country, the results would be biased. Data wrangling tools can simplify application of these strategies. Pre-processing is closely tied to feature engineering, and you might find overlap in how different ML tools or references categorize pre-processing activities compared to feature engineering activities. The goal of preparing data is to provide a clean, balanced data set that the desired algorithm can use and will produce accurate results. Pre-processing focuses on getting the data set to where the data scientist can perform the more advanced feature engineering tasks. A pre-processing task for the fraud detection example might be to convert the Y or N in the "is this fraud" field to a numeric equivalent, such as 1 for yes and 0 for no. This task can simplify the algorithm's ability to work with the field. Data exploration typically begins with desktop tools, including Excel and database access tools. But often, data scientists will use interactive Jupyter notebooks with tools such as Pandas and PySpark to develop visualizations of the data. Pandas is an open-source data analysis and manipulation tool that is built on top of the Python programming language. PySpark is the Python API for Apache Spark, and it provides a shell to interactively analyze data in an Apache Spark environment. This type of analysis provides the data scientist with insights to help them decide what is important and can provide insight into feature engineering. For example, a data scientist might use a clustering algorithm to identify categories within the dataset, such as customer segments. Clustering algorithms are an important part of unsupervised learning models, but can also be applied to data exploration. The clustering can inform how features are prioritized or what type of additional feature engineering might be needed to make the dataset more useful. Here are a few key points to summarize this section. The goal of data preprocessing is to start preparing the data for training. The data scientist usually does pre-processing, and they would usually explore the data and perform visualizations to help them identify what needs to be changed. They might use a variety of strategies during pre-processing. This section describes the feature engineering task within the prepared data step of the ML lifecycle. Feature engineering is a process to select and transform variables, features, in the dataset to improve how the selected algorithm can use them. Feature engineering is also used to improve the accuracy and performance of the model. Data scientists apply domain knowledge and statistical modeling to perform feature engineering. In some cases, the feature engineering step itself can use machine learning to perform feature engineering. The tasks of feature engineering include feature creation, transformation, extraction, and selection. The next two slides provide examples for these steps. Feature creation and transformation are both processes that generate new features from existing features by using different types of statistical modeling techniques. For example, one feature creation technique is called binning. With binning, you convert continuous data into groups, also called bins. By grouping the items, you provide a fixed number of values to work with, which is easier for the algorithm to work with. Dimensionality means the number of features that your dataset has. High-dimensional data is data in which the number of features is close to or larger than the number of data points. When a dataset has many different dimensions of data, many features, to sort through, models will have a difficult time finding the patterns that you want them to identify. Therefore, performing feature extraction and selection is important. An example of feature extraction is removing certain parts of speech, such as articles and prepositions, from a natural language processing dataset. Feature selection means removing features that don't appear to have a high value in predicting the outcome or that are mostly redundant to another feature that could provide the same input. A domain expert might look at a set of features and be able to identify items that would not be relevant to the business problem. In the insurance fraud example, the same domain expert who helped to provide the dataset and label the fraudulent items suggested that the umbrella limit is not a particularly useful field when it comes to insurance fraud, so that feature could be removed. Here are a few key points to summarize this section. The feature engineering step is about using the existing features and improving their value for the model. This might include feature creation and transformation to add new values or features. It might also include feature extraction and selection, which are techniques to reduce the dimensionality of the dataset, to make the dataset easier for the model to process. This section describes the develop model phase of the ML lifecycle. Model development consists of model building, training, tuning, and evaluation. This process is the heart of machine learning. Model building includes building the algorithm and its supporting code. The code building process should follow best practices that apply to any software development project. ML frameworks are available to help developers build and train models. The ML model learns through a repetitive training process by examining features to find patterns, making predictions on those patterns, and evaluating the quality of the predictions. The time and resources that are required to train the model are related to the type of model you're running and the data set that you're using to train the model. For example, a deep learning model would require higher levels of training than a supervised learning model that gives a binary prediction like, is this fraud, yes or no? By monitoring errors during the training process, the model improves its understanding of the feature patterns that lead to the correct target values. Each pass through the model allows the tuning of parameters, tweaking the weights of how important the different features are, and then seeing if that makes the results better or worse. You measure the error rate of each pass to evaluate the accuracy of the model. A data scientist would iterate on training and tuning the model until the error rates indicate that the model is accurate enough for the business problem. For example, the business might determine that the predictions need to be correct 80% of the time to meet their goals. After you've tuned your model to the accuracy level that is expected for the business problem, it's time to run the model with the test dataset to validate the model's accuracy beyond the training dataset. For testing, you remove the known label off of the test dataset, feed the test data through the model, and evaluate its predicted values compared to the actual label values. Based on the results of training, tuning, and evaluating the model with test data, the data scientist might fine-tune the data, the algorithm, or both. If the results are acceptable, the model is ready to be deployed. The actual metrics and methods for tuning the model are much more complex than described in this course, but here are a few general metrics that you should be familiar with. Accuracy is the base metric that's used to evaluate a model, and it's the measure of the number of correct predictions when compared to all predictions made. Other measures incorporate data about how many times the model positively predicted the presence of a target and how many times it predicted the absence of the target. A true positive is when the model predicts that the target exists and it's correct. For example, the model says this is a dog and the picture contains a dog. A false positive would be when the model predicts there's a dog, but there isn't, it's a cat. A true negative means the model correctly predicted that the target is not present. It doesn't identify a bear as a dog. And a false negative would mean that the model did not identify the target, but should have. Precision is a measure of how many true positives were predicted out of all the positive predictions that the model made. For example, your model made 100 positive predictions about a dog, but only 50 of them were actually dogs. Recall measures how many times the model predicted true positives compared to how many actual positives exist in the data. For example, maybe your model got 50 true positives of dogs, but also missed 150 dogs that it should have predicted. The F1 score is a combination of these two approaches, and it's often used as a quick validation of a model. The process of building, training, and tuning the model is resource intensive, and the model development environment requires an infrastructure that is designed for ML processing. To train and tune your model, you need compute, networking, and storage resources. In addition to the characteristics this course discusses, such as the volume, velocity, and type of data to be processed, the complexity of the model and the algorithm that you use will also influence what type of infrastructure you need. Choosing GPU-based instances can help you train models faster, which enables data scientists to iterate faster, train more models, and increase accuracy. Training activities often run on big data frameworks, such as those described in the Processing Big Data module. Clustered big data configurations provide high-volume, parallel processing of a lot of data at one time, and they're good for calculations that can be split up and worked on in pieces, loosely coupled. An example of an ML problem that might take this approach is genomics. In genomic ML, a researcher might iterate on a dataset, tweaking parameters and optimizing thousands of times. For this type of work, a big data solution can speed up the parallel processing of those iterations. Another cluster-based configuration that is often used for training ML models is high-performance computing, or HPC. HPC is also a clustered solution, but it's optimized for compute-intensive operations, where the computations are tightly coupled, meaning the work can't be distributed into individual tasks. With HPC, the single computation can be spread across many instances in a cluster. A weather researcher who is developing a model of weather across the US would use an HPC system for models. But bigger is not always better. Simple models might not train faster on larger instances because they might not be able to benefit from increased parallelism. These models might even train slower because of the high communication overhead of GPUs. The ML infrastructure on AWS section describes the types of infrastructure choices and services that can help you match resources to the scale that you need and the cost that you're trying to manage. As a best practice, start with smaller instances and scale as necessary. Here are a few key points to summarize this section. Model development is at the heart of machine learning. The model is trained and tuned until it reaches the desired accuracy level. Test data is then used to validate results with a subset of data that's not labeled. You need to right-size your resources for the training phase, which is resource-intensive. Often, big data frameworks or HPC systems are used to train models. This section describes the deploy model phase of the ML lifecycle. After you've trained and optimized your model to your desired level of accuracy and precision, you put it into production to make predictions. Standard debugging and logging of the application are part of monitoring the deployed model. You want to capture normal application metrics and track items such as slow queries, high latency, and problem events. However, monitoring the model's output in production is critical to ensure that the model is producing the expected level of accuracy with production data. By monitoring the model, you can also adapt to changes in data patterns that might cause the model to become less accurate over time. From a purely operational perspective, there might not be errors, but that doesn't mean that the model is performing as it needs to. Typically, roles that differ from those who ingested and prepared the data or trained and tuned the model will deploy the model into production. Inference is the process of making predictions on the production data. The code and infrastructure that are related to production are referred to as inference. Notably in production, the model takes in individual samples and provides an output. Compare this to the training environment where the model churns through high volumes of transactions in parallel. As with any application, you want to ensure that it performs as expected in production while managing the cost to operate it. Importantly with ML applications, the choices that you make to train the model differ greatly from those to put it into production. Training jobs batch process hundreds of data samples in parallel, and inference jobs usually process a single input in real time. Therefore, training the model typically requires much higher levels of compute power than the deployed model. Aside from selecting resources to deploy the model, scaling your ML solution means building your environments with infrastructure as code and automating the ML deployment pipeline. You want to be able to respond quickly to changes without a lot of human interventions. This module has looked at each of these steps on its own, and each of them might be performed by different teams who use different resources and infrastructure. But when you need to update the ML solution, you need to reflect updates across all the integrated steps. The 4 different sets of activities that are numbered in this diagram highlight flows that are involved in an update. In this example, if you want to incorporate additional data into your training data set and retune the model, you'd need to initiate the following flows. The data engineer extracts and loads the additional data into the lake. The data scientist brings the new data into the processing phase and then saves any updates to the data and the features. The data scientist then trains and tunes the model by using the updated features and data and saves the updated model version. The ML operations team retrieves the latest model and deploys the latest code to the production environment. Each process relies on different sets of infrastructure that someone is responsible for maintaining, optimizing, and securing access to. This includes the resources that are required to extract and load the data into the lake, the processing environment where the data is prepared for training, the model development environment where the model is trained, and the production environment where the model is deployed. Depending on how your organization assigns these responsibilities, deploying updates to an ML solution can quickly become complex to manage. Automation of these processes not only streamlines updates, but reduces the chance of human error across these integrated activities. DevOps is the combination of cultural engineering practices and patterns and tools that increase an organization's ability to deliver applications and services at high velocity and better quality. Over time, several essential practices have emerged when adopting DevOps. Continuous integration and continuous delivery, or CI/CD, infrastructure as code, and monitoring and logging. Like DevOps, MLOps relies on a collaborative and streamlined approach to the ML development lifecycle. The intersection of people, process, and technology optimizes the activities that are required to develop, build, and operate ML workloads. MLOps focuses on the intersection of data science and data engineering in combination with existing DevOps practices to streamline model delivery across the ML development lifecycle. MLOps requires the integration of software development, operations, data engineering, and data science. The Automating the Pipeline module goes into greater detail about tools and processes to automate data pipelines. Here are a few key points to summarize this section. When the model is deployed into production, the infrastructure typically has different characteristics than the training environment. The code and infrastructure that are related to the production model are referred to as inference. The large number of roles and different environments that are part of the ML lifecycle need an automated deployment strategy. MLOps is a best practice that provides an approach to create a collaborative and streamlined approach to deployments. This section describes the AWS services that provide an ML infrastructure. The slide graphic illustrates 3 layers of ML services offered at AWS. The key is to understand the types of tools that each layer provides and to determine the appropriate combination for your use case, your team members, and organization. Some services are designed specifically for machine learning, including Amazon SageMaker, AWS Deep Learning AMIs, AWS Deep Learning Containers, and Amazon Elastic Inference. Other services work well for common ML requirements, including big data or HPC, GPU-based compute, and low-cost fast storage. The bottom layer shows examples of compute, networking, and storage services that make up the foundational blocks of ML infrastructure. If you choose to build and manage your own infrastructure, these are the types of services that you would use to host your ML infrastructure. The middle layer highlights ML frameworks that the AWS ML infrastructure supports. These frameworks make it easier for developers to build and deploy ML models. The top layer contains workflow services. These make it easier for you to manage and scale your underlying ML infrastructure. The next slides look in a bit more detail at key services that are related to this course. SageMaker is discussed in the section after this one. A link to the AWS Machine Learning Infrastructure page is provided in the course resources. The services that are described here all help to provide the compute power and speed that are needed for ML applications. Amazon Elastic Compute Cloud, Amazon EC2, has instance types that are especially suitable to ML applications. The P3 and P4 types are GPU-based and provide high-performance compute to train ML models. The G4 and INF1 instance types are well-suited to running inference on deployed models. With the Elastic Inference Service, you can attach low-cost GPU-powered acceleration to other EC2 instance types to reduce the cost of running deep learning inference. Elastic Fabric Adapter is a network interface that provides a low-latency connection between instances in a clustered configuration. This can help ML models to train faster. The storage services that are described here provide for the size, type, and speed of processing that are required to develop models. You can choose the types of storage that suit your use case. Amazon S3 provides object storage, Amazon Elastic Block Store or Amazon EBS provides block storage, and Amazon Elastic File System or Amazon EFS provides file system storage. Amazon FSx provides storage for high-performance file systems such as Lustre. These services from the Workflow Services layer help to simplify the work that's required to build an ML environment. The first two, Deep Learning AMIs and Deep Learning Containers, are specifically designed for deep learning. Amazon Elastic Container Service, Amazon ECS, and Amazon Elastic Kubernetes Service, Amazon EKS, are 2 options for managing container deployments. These services from the Workflow Services layer help to simplify building a big data or HPC system for ML model training. Amazon EMR is covered in detail in the Processing Big Data module. AWS Batch is an orchestration service that can run complex training jobs on a schedule. The service chooses just enough compute resources to run the job and then shuts them down when the job's complete. AWS Parallel Cluster is an open-source cluster management tool that simplifies deployment of HPC clusters. Here are a few key points to summarize this section. The AWS ML infrastructure services are grouped into 3 layers, with the compute, networking, and storage at the bottom, and workflow services at the top. In the middle are popular frameworks that are integrated with the AWS ML tools. The workflow services help to simplify creating and managing ML environments. This section introduces key features of Amazon SageMaker. SageMaker includes features and tools that you can explore for ML projects, such as SageMaker Studio, SageMaker Data Wrangler, SageMaker Processing, and SageMaker Canvas. Amazon SageMaker Studio provides an integrated development environment, or IDE, for ML, from which you can build, train, deploy, and analyze models all from the same application. Amazon SageMaker Data Wrangler is a feature of SageMaker Studio, and you can use it to ingest data, explore it, perform pre-processing steps, and perform feature engineering. The tool includes standard transforms for cleaning and feature engineering and can automatically generate insights about data quality and abnormalities. You can also define a workflow of wrangling steps to be performed. This provides a low-code way to do a lot of the common data preparation steps. The Processing Big Data module introduces the concept of coding using Jupyter notebooks. SageMaker Studio notebooks are collaborative notebooks that you can launch quickly because you don't need to set up compute instances and file storage in advance. SageMaker Studio notebooks provide persistent storage, which enables you to view and share notebooks even if the instances that the notebooks run on are shut down. A SageMaker Studio notebook runs in a managed environment that includes a configurable EC2 instance and a container image with the files that are needed to run the notebook. Amazon SageMaker Processing is a tool to analyze data and evaluate ML models. With processing, you can use a simplified managed experience on SageMaker to run your data processing steps, such as feature engineering, data validation, and model evaluation. You can choose to put your code on built-in data processing containers or bring your own containers and submit custom jobs to run on the SageMaker managed infrastructure. SageMaker comes with a suite of built-in algorithm choices as well as pre-trained models and pre-built solution templates to help data scientists start to train and deploy models quickly. For deploying your ML models, SageMaker provides the option to deploy using a hosted endpoint that's suitable for real-time inference where you want to make one prediction at a time. To train a model in SageMaker, you create a training job. The diagram on this slide shows the AWS services that are used to run a training job and deploy it to production. SageMaker Hosting hosts an endpoint where applications can access the model and have it predict an outcome when given an individual request. After you create the training job, SageMaker launches the ML Compute instances and uses the training code and the training dataset to train the model. The service saves the resulting model artifacts and other output in an S3 bucket that you specify. SageMaker gets the training image for your selected algorithm from a container that's available through Amazon Elastic Container Registry, or ECR. The ML Compute instances and the SageMaker endpoint are directly managed within SageMaker. SageMaker is integrated with Amazon S3 and Amazon ECR to simplify using those resources for training and deployment. SageMaker has been designed to abstract a lot of the work that's required to support ML workloads. By using the service, data engineers and data scientists can focus on the goals and outcomes. SageMaker Canvas takes the abstraction to another level and provides an interface where a business analyst who isn't a data scientist can create models and get predictions. A business user can select a file and preview its data before uploading. Then, they can choose a target column and a recommended model and preview and build the model. This lets them quickly review the results and make predictions on new data by record or by batch. Here are a few key points to summarize this section. SageMaker is a managed service with tools and features that work across the ML lifecycle. SageMaker Studio provides an integrated IDE and provides access to other SageMaker features in one place. With SageMaker Hosting, you can deploy real-time inferencing or use batch transform to process inferencing on a whole data set as a batch. SageMaker Canvas gives business analysts the power of ML without having to code at all.